as the parameter to this method. We are saying that after the calculations are performed by the CPU-bound operations, don't return to the main thread. So, for example, a context where this would be appropriate would be once the calculations are completed, we want to save the calculated data to a file. So in this scenario, we don't want to display the data on, for example, a stock market chart. We only want to save the data locally. In this context, there's no reason to return to the main thread. However, in a context where we need to display the information on a chart, we of course would need to return to the main thread. The last best practice I would like to include in this video is that we should avoid including the task.run method within methods implemented in server-side components. If, for example, we implemented our trading platform calculation functionality as a software-as-a-service application for the purpose of providing calculated technical indicator information to web-based client trading platforms, we should not implement these CPU-bound operations using the task.run method. On the surface, it may seem like this would give us a performance advantage, but in reality, this puts an unnecessary strain on server resources and ultimately can adversely affect performance. The reason for this is that with a server-side component, say for example implemented as an ASP.NET Web API component, you may have thousands of HTTP requests coming in to the relevant Web API component. Each HTTP request requires a thread from the server's thread pool. If the code within the relevant server-side method is coded to run 4 operations asynchronously through the use of the task.run method, then your Web API component needs to acquire an additional 4 threads to carry out the instructions implemented in the relevant method. This could cause an unacceptably high use of server resources, which could adversely affect the overall performance of the relevant server and ultimately negatively impact the user's experience with the relevant application. So the moral of this story is avoid running additional background threads on the server side. Rather run CPU-bound operations synchronously on the server side. You can still ensure that the client-side UI is responsive by calling the server-side code using async await. Remember, an HTTP request from the client's perspective is an IO-bound operation. Note that running IO-bound operations on the server is different to running CPU-bound operations on the server. An example would be downloading the raw stock market data from the server. Perhaps the server-side code simply retrieves the raw stock market data from a database before returning the relevant data to the client. This IO-bound operation can be written on the server using async await. The IO-bound code does not require additional threads and therefore additional server-side resources. When a client request is made to run the method responsible for running the relevant IO-bound operation on the server, the thread used for processing the request can be released to handle other requests while the relevant IO-bound operation is being performed. CPU-bound operations that are invoked using task.run will require additional threads, which means additional server resources will be required. In summary, when it comes to best practices in terms of asynchronous programming in C#, know the nature of your asynchronous code. Ask the question, is the operation CPU-bound or IO-bound, and then apply the relevant asynchronous code appropriately. Avoid writing CPU-bound operations within reusable library components using the task.run method. Let the consumer of the library component choose whether to run the CPU-bound operations synchronously or asynchronously. Methods that run IO-bound operations asynchronously, included within reusable library components, should include the async suffix as part of the relevant method's name. This will let the consumer of your library know that the relevant method should be run asynchronously using async await. On the client side, run CPU-bound operations close to the relevant UI event handler method. For example, use the task.run method directly within the relevant button-click event handler method. If, for example, a button-click event handler method needs to perform a CPU-bound operation asynchronously on a background thread, and subsequently code within that method does not require a return to the UI thread, explicitly let the .NET runtime know that it is unnecessary to return to the UI thread once the CPU-bound operation has completed, by appropriately calling the configure-await method. This can result in a performance boost. Avoid running CPU-bound operations on the server side using the task.run method. These operations require additional threads, which can result in a strain on server-side resources, and the issue will be compounded if the server is handling hundreds or thousands of HTTP requests. Running IO-bound operations, for example, retrieving information from a web API component, reading data from a database or writing data to a database on the server side using async await, is good practice because the main thread of execution is free to handle other client requests while the relevant IO-bound operation is running. So in this video, we covered how to implement best practices in our code when running code asynchronously in C#. For more content on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future videos released from this channel. If you feel you've gained value from viewing this video, please smash the like button. It will be greatly appreciated. Please feel free to share any of the videos created by this channel with anyone you feel may benefit from their content. I love reading your comments, so please feel free to share your thoughts with me in the comments section. All code created in these videos can be downloaded from GitHub. Please see below in the description links to the appropriate GitHub repository. Hi and welcome to the fourth and final video in a video series on asynchronous programming in C#. This video is also part of the 6th tutorial in an advanced C# course. This video is a continuation of the last 3 videos in this video series on asynchronous programming, so please view each of the preceding videos in this video series before viewing this video. In this video, we are going to look at how to use a cancellation token source object to explicitly cancel an asynchronous task or many asynchronous tasks in code before the relevant task or tasks have completed using one cancellation token source object. For more content on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future content released from this channel. Right, so to gain an understanding of how we are able to implement code to cancel one asynchronous operation or multiple asynchronous operations using one cancellation token source object, let's look at a practical code example. So I'm going to base this code example on an example included in the Microsoft Docs. So please navigate to this URL. A link to this URL has been included below in the description. You can see that this web page is entitled Cancel a List of Tasks, in brackets C#. So let's first look at the prerequisites section of this document. I want to draw your attention to the first prerequisite. So this tutorial requires the following: .NET 5 SDK. I'm actually not going to install the .NET 5 SDK on my Windows platform at this time, and we'll be creating this example using the .NET Core version 3.1 runtime. We are able to run this example using the .NET Core version 3.1 runtime, but we will need to make a small modification to the code to get this working. If you do decide to install the .NET 5 SDK, know that the version available at the time of writing this tutorial is not yet the official release. It is an RC release, which stands for Recommended Candidate. So if you install .NET 5 SDK, I recommend reading all associated content that can be found at this URL, that we can navigate to when we click the link here marked .NET 5 or later SDK. This content can guide us in, for example, which version of Visual Studio should be installed to support the current RC version of .NET 5. I also recommend reading this blog post posted by Richard Lander. This blog post can be found at this URL. For a foundational understanding of .NET 5, I recommend viewing a video created by this channel, which can be found at this URL. As always, I have included all relevant links below in the description. I'll demonstrate how we are able to implement and run this code example, so even if you decide not to install .NET 5 SDK at this time, and your latest version of the .NET runtime is .NET Core version 3.1, you are still able to follow along with the implementation of this example. To enable running this code using the .NET Core 3.1 runtime, we only need to apply one simple code modification. We'll apply this modification when appropriate. Let's look at the first paragraph on this web page. In the first paragraph on this web page, it states, you can cancel an asynchronous console application if you don't want to wait for it to finish. By following the example in this topic, you can add a cancellation to an application that downloads the contents of a list of websites. You can cancel many tasks by associating the cancellation token source instance with each task. If you select the Enter key, you cancel all tasks that aren't yet complete. So we are going to base our practical code example on the example here provided in this web page in the Microsoft Docs. However, we are going to implement our code example as a UWP, Universal Windows Platform project, instead of how it is implemented in this Microsoft example as a .NET Core console application. We are going to copy aspects of the code provided in the Microsoft code example over to our code editor in a step-by-step fashion. So let's create a UWP project and let's name our project Cancel Download Async Operations UWP. Let's set up a basic UI, user interface. So let's start by dragging a button onto our designer surface. Let's name this button BTN Cancel Download, and let's label this button Cancel Download. Let's drag another button onto the designer surface just below the button we have just added. Let's name this button BTN Download Content. Let's label this button Download Content. Let's drag a list view control onto the designer surface and position it so that the contents of the list view control will appear to the right of our buttons. Let's name this list view control LVW Output. So let's access the main page.xaml.cs file to add the relevant functionality for our UI. Firstly, let's ensure that we include all the relevant using directives. Let's copy them from the relevant section of the relevant Microsoft web page and paste them into our code editor like this. Let's then copy and paste the relevant fields like this. These fields contain an object reference variable of type cancellation token source that will be used to cancel the relevant asynchronous tasks, a collection of URLs of type IEnumerable that will store the addresses of the web pages that will be downloaded by the relevant asynchronous operations, and an object reference variable of type HTTP client that will handle the connection to the relevant web pages and also handle the download functionality. So in our application, these fields don't need to be static. So let's remove the static keywords. Let's read the explanation provided under the relevant code fragment containing the fields we have just copied. The cancellation token source is used to signal a requested cancellation to a cancellation token. The HTTP client exposes the ability to send HTTP requests and receive HTTP responses. The s_URL list holds all the URLs that the application plans to process. So the next section of the Microsoft web page is an explanation of the code within the entry point of the application, i.e. the main method. As discussed, the Microsoft code example is based on the .NET Core Console project template. We are basing our application on the UWP Universal Windows Platform project template, so our code implementation will be slightly different. So the main difference between our code and the Microsoft example is that the Microsoft example is implemented so that when the user presses the Enter key, this action will trigger the cancellation of the relevant operations, i.e., the operations responsible for downloading the contents of a collection of web pages. The UWP project template makes our code implementation simpler because we can leverage a button-click event handler for this purpose. So in this Microsoft example, the tasks responsible for downloading the content and outputting the relevant information about the content are invoked through a call to the method named SumPageSizesAsync. The cancellation functionality is handled in the code above this method call. The method is implemented through a Lambda expression here. Code is implemented here using the WhenAny method. The WhenAny method basically accepts an array of task objects. So the SumPageSizesAsync method returns a task, and the relevant Lambda expression responsible for the cancellation functionality is run using the task.run method, which also returns a task object. Then an array containing a task object encapsulating the cancellation operation, as discussed, this is implemented as an asynchronous method in the form of a Lambda expression, and the download operation, which is implemented as a named method, are passed into the WhenAny method. The task.WhenAny method will complete when any one of the operations passed within the relevant array argument completes. This means that if the user presses the Enter key before the download operation, i.e. which is invoked by the call to the SumPageSizesAsync method, completes, this will effectively cancel the asynchronous web page download operations and associated functionality, for example, summing up the number of bytes downloaded, etc. So we used the WhenAll method in the previous video, which allowed us to run a collection of tasks in parallel without blocking the main thread. The WhenAny method is similar, but the difference is that the WhenAll method completes when all the relevant operations have completed. The WhenAny method completes when any one of the relevant operations have completed. Like the WhenAll method, the WhenAny method does not block the main thread. So this means that in the context of the Microsoft example here, if the user presses the Enter key before the operations invoked by the SumPageSizesAsync method complete, this will result in the downloading operations being cancelled. The cancellation operation will complete before the download operations complete, resulting in the download operations being cancelled. So we are going to implement similar code within our example. The difference is that we'll implement a cancellation button to enable the user to cancel the download operations by pressing the cancellation button, rather than implementing code to allow the user to press the Enter key for this purpose. With our UWP project, we have the benefit of a rich user interface. So let's go to our code behind class, i.e. the mainpage.xaml.cs file, and write a private method that will encapsulate the functionality to add a list item to our list view control, i.e. the control we have named LVW_output. We have already written a private method encapsulating this functionality in our previous example, So let's navigate to the relevant GitHub repository and copy this private method. This URL has been included below in the description. So here we can see the relevant method named addListItem. Let's copy this method to our clipboards and appropriately paste this method within our mainpage.xaml.cs file. So we can now write the code to handle the button click events. Let's start with the download functionality. First, let's create two private methods that are responsible for downloading the relevant content, calculating the size of the relevant content, and outputting status information to the user regarding the relevant downloaded content. So in the Microsoft Docs web page, let's look at the section entitled Create the Asynchronous SumPages Sizes method. Let's copy this method and appropriately paste the method within our mainpage.xaml.cs file. In our example, this method does not need to be static, so let's remove the static keyword from the method definition of the SumPageSizes async method. And let's include the private access modifier within the SumPageSizes async method's method definition. The next thing we need to modify in our example for the SumPageSizes async method is where the code writes text to the console screen. Our output will be added to the list view control that we named LVW output. So let's replace the console.write methods with a call to our private method named addListItem. We can remove the \n character sequences from the relevant text because we don't need a line feed, due to the fact that we are adding each item of text as its own item within the list view control. Let's read the brief description of this method provided within the relevant Microsoft web page. The method starts by instantiating the starting of a stopwatch. It then loops through each URL in the s_URL list and calls process URL async. With each iteration, the s_cts.token is passed into the process URL async method, and the code returns a generic task where tResult is an integer. So within the relevant Microsoft web page, let's look at the section entitled Add Process Method. So the first line in this section reads, add the following process URL async method below the SumPageSizes async method. So let's copy the process URL async method to our clipboards like this and appropriately paste it within the mainpage.xaml.cs file like this. Let's remove the static keyword from the process URL async method's method definition. Let's include the private access modifier within the process URL async method's method definition. Let's replace the console.write method with the addListItem method, like this. And if you'll remember, before we started implementing this example, I spoke about one of the prerequisites for creating this code example. The prerequisite being the installation of the .NET 5 SDK. So this is the only line of code that doesn't work if we do not have the .NET 5 SDK installed, and if we are running this example using the .NET Core 3.1 runtime. So if you are running this project using the .NET Core 3.1 runtime, simply remove the argument named token from the line of code that calls the response.content.readAsByteArray async method. So let me just say that it is preferable to pass in the token argument to this method, but if you don't wish to install the .NET 5 SDK at this time, we are still able to run the code by removing the token argument. This is not ideal, but we are still able to gain an understanding of the cancellation token source object and how we are able to cancel one or more asynchronous operations using one cancel token source object. Let's read the explanation of this method in the relevant Microsoft web page. For any given URL, the method will use the client instance provided to get the response as a byte array. The cancellation token instance is passed into the http client.getAsync and http content.read as byte array async methods. The token is used to register for requested cancellation. The length is returned after the URL and length is written to the console. So obviously where it says the URL and length is written to the console, in our example, we are instead adding the relevant text to our list view control. Okay, so let's implement the code for the button that invokes the download operations. Let's go to our designer surface and double-click on the button labeled Download Content. Let's implement the code that calls the awaitable SumPageSizesAsync method to perform the downloading of the relevant content, the calculation of the size of the content, as well as the outputting of the relevant information about the content to our list view control. So in order to call this method asynchronously, we need to include the await operator. We also need to include the async modifier within the method definition of the relevant button click event handler. Let's implement the cancellation functionality. Let's go to our designer surface and double-click on the button marked Cancel Download. Within the relevant button click event handler, let's implement the cancellation functionality. To add the operation, we can simply call the cancel method on the relevant cancellation token source object, like this. Okay, let's run the code. Firstly, let's demonstrate what happens when we click the Download Content button. So let's allow the operations to complete so we can see what happens when we don't cancel the operations. We can see that the appropriate output is presented to us as each operation completes. When the content for a particular web page has been downloaded, the web page URL followed by the number of bytes downloaded is presented on our list view control. And then once all the operations have completed, we are presented with the total number of bytes downloaded as well as the time that has elapsed between the time when we started to download the content and the time that the relevant download operations completed. Great! So let's run the code again. Let's click the Download Content button, and we are presented with the relevant output in our list view control as expected. Right, let's see what happens when we press the Cancel button. And a runtime error occurs. So in order to handle the cancellation operation appropriately, we need to handle a particular type of exception. So when the cancel method is called while the asynchronous operations are running, an exception of type task cancelled exception is thrown. So we can simply include our code that calls the SumPageSizesAsync method within try-catch code like this, and handle the task cancelled exception appropriately. So we could access the thrown exception object to access details about the exception, but in this case, we only want to output status information to the user that the operations have been cancelled. So let's do this. Let's simply add the literal text, download operations cancelled. So remember, we are passing a token object as an argument to the getAsync method here in the process URL async method. The process URL async method is called within a loop from within the SumPageSizesAsync method. This token object allows us to trigger a cancellation of all running asynchronous tasks that reference this token object. When the cancel method is invoked on the relevant cancellation token source object, an exception of type task cancelled exception is thrown, and we can appropriately handle this exception in our code. Right, let's run the code. So let's click the Download Content button, and we are presented with the relevant output as expected. So let's see what happens when we cancel these operations. And there we have it. The task cancelled exception is thrown when the cancel method on the cancellation token source object is invoked, and we are handling the thrown exception in our custom way, i.e., in a way that suits our application. So we can see the output text, download operations cancelled, which is an expected result. Okay, so we are also able to automatically cancel the operations after a predefined duration of time. So let's say we wanted our download operations to be cancelled if they haven't completed within a specific time duration. The way we can do this is by calling the cancel after method on the relevant cancellation token source object. We can call this method before the relevant operations are invoked, like this. We need to pass in the duration of time in milliseconds to the cancel after method. This number represents the time elapsed from the moment the relevant operations are invoked. So let's specify 3,500 milliseconds or 3.5 seconds. Let's run the code. And you can see that after 3.5 seconds, the relevant operations are automatically cancelled. So you can see how this functionality can be useful when we want to automatically cancel an operation or operations after a specified amount of time. Great! For further information about asynchronous programming in C#, I recommend reading relevant content provided in the Microsoft Docs. So to summarize, in this video series, we looked at Microsoft's recommended approach for implementing code to run an operation or multiple operations asynchronously, namely the task-based asynchronous pattern. We discussed that running certain relatively long-running CPU blocking operations can adversely affect the performance of our applications. To alleviate these negative effects on user experience, UX, we can run these relatively long-running CPU blocking operations asynchronously. In order to implement the asynchronous code correctly, we first need to know the nature of the operations that we wish to run asynchronously. We need to first ask the question, is the relevant operation a CPU-bound operation, or is the relevant operation an I/O-bound operation? In the first part of this video series, we focused on running I/O-bound operations asynchronously using the async modifier, the await operator, and the task or generic task object. In the second part of this video series, we looked at running CPU-bound operations asynchronously using the task.run method to run operations on background threads. We also looked at the task.waitAll method. In the third part of this video series, we looked at best practices when implementing operations in C# to run asynchronously. We also looked at the task.whenAll method and how it differs from the task.waitAll method. In this video, which is the final part of this video series, we looked at how we can provide the user with the ability to cancel one or more running asynchronous operations before the relevant operations have completed using one cancellation token source object. We also demonstrated how we can automate the cancellation of running asynchronous operations after a specified amount of time by calling the cancel after method on the relevant cancellation token source object. I hope you have enjoyed the final video in this video series on asynchronous programming in C#. The next topic in this advanced C# course will be LINQ, Language Integrated Query. For more content on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future content released from this channel. If you feel you have gained value from this video, please hit the like button. It will be greatly appreciated. Please feel free to share any videos released from this channel with anyone you feel may benefit from their content. I really enjoy reading your comments, so please feel free to share your thoughts with me in the comment section. As always, the code in this tutorial can be downloaded from GitHub. A link to the relevant GitHub repository has been included below in the description. Hi and welcome to the first part of a video series on LINQ. This video is also the first part of the 7th tutorial in an advanced C# course. Later in this tutorial, we'll look at a code example to help with our understanding of LINQ. But let's first answer the question, what is LINQ? LINQ stands for Language Integrated Query. LINQ is defined in the Microsoft Docs as the name for a set of technologies based on the integration of query capabilities directly into the C# language. LINQ was originally released as a major part of .NET Framework 3.5 in 2007. Here is a paragraph from the Microsoft Docs which provides an excellent overview of what LINQ is. Language Integrated Query, LINQ, is the name for a set of technologies based on the integration of query capabilities directly into the C# language. Traditionally, queries against data are expressed as simple strings without type checking at compile time or IntelliSense support. Furthermore, you have to learn a different query language for each type of data source: SQL databases, XML documents, various web services, and so on. With LINQ, a query is a first-class language construct, just like classes, methods, events. You write queries against strongly typed collections of objects by using language keywords and familiar operators. The LINQ family of technologies provides a consistent query experience for objects, LINQ to objects, relational databases linked to SQL, and XML, LINQ to XML. Note that you can write LINQ queries in C# for SQL Server databases, XML documents, ADO.NET datasets, and any collection of objects that support the IEnumerable interface or the generic IEnumerable interface. So, for example, you can perform LINQ queries against collection types like an array, generic list, generic dictionary, generic queue, generic stack, etc. Basically, any collection type that implements the IEnumerable interface or the generic IEnumerable interface. LINQ support is also provided by third parties for many web services and other database implementations. You can create custom providers using iQueryable. Custom providers will not be discussed in detail in this video series. If you would like to learn more about implementing your own custom provider, please navigate to this URL. In this video series, we'll primarily focus on LINQ to objects and LINQ to entities. LINQ to entities provides language integrated query, LINQ, support that enables developers to write queries against the Entity Framework conceptual model using either Visual Basic or Visual C#. So, Entity Framework Core is a modern object database mapper for .NET. It supports LINQ queries, change tracking, updates, and schema migrations. Entity Framework Core, or EF Core, can be used to work with many databases, including SQL databases, on-premises and Azure, SQLite, MySQL, Postgres, and Azure Cosmos DB. In this video series, we won't look at LINQ to dataset or LINQ to XML. Please navigate to this URL for more information on LINQ to dataset, and please navigate to this URL for more information on LINQ to XML. To get started with LINQ, in this video we'll focus on LINQ to objects so that we can first get a basic idea of what the implementation of LINQ looks like in code and how it can be used for querying C# collections. So in the spirit of cross-platform development, I've decided to demonstrate this code example on my Mac platform using Visual Studio 2019 for Mac Community Edition. If you have a Mac platform and wish to follow along on your Mac and you don't yet have Visual Studio installed, You are able to download and install Visual Studio Community Edition 2019 free of charge from this location. All links mentioned in this video are available below in the description. If you are using a Windows OS, please don't let the fact that I'm using a Mac platform put you off following along with this tutorial. In terms of the code example that we'll create in this video, the coding experience using Visual Studio for Mac is almost exactly the same as the coding experience using Visual Studio for Windows, so this should not be a barrier for a learner to follow along with this demonstration. If you haven't yet installed Visual Studio 2019 on your Windows platform, please view a video created by this channel, which provides a guide to installing Visual Studio 2019 Community Edition free of charge. So firstly, let's create a .NET Core console application. Let's name this project the Pretend Company application. Before we write calling client code in the main method, we are going to add two standard library projects. Let's first add a standard library project named TCP Data. Let's then add another standard library project named TCP Extensions. So let's now go to our project that we named TCP Data. Let's delete the class that has been automatically generated for the TCP Data project. Let's add a new class named Employee. Let's add 6 auto-implemented properties to the Employee class. ID as int, first name as string, last name as string, annual salary as decimal, isManager as boolean, and lastly, department ID as int. Let's add another class to the TCP Data project. Let's name this class Department. Let's add 3 auto-implemented properties to our Department class. ID as int, short name as string, and long name as string. Let's add a class named Data to our TCP Data project. Let's make this class a static class. So let's add 2 public static methods to the Data class. Let's first create a static method named getEmployees, which returns a generic list strongly typed as employee. Let's ensure that we include the appropriate using directive for the use of generic list objects at the top of our code editor. So let's include a using directive to the system.collections.generic namespace, like this. Let's write the code to add some made-up employee records to a generic list that is strongly typed with the user-defined type employee. Let's write code to return the list of employee records to the calling client code. Let's add another static method, and let's name this method getDepartments. This method also returns a generic list object, but this generic list object is strongly typed as department. Let's write the code to add some made-up department records to a generic list that is strongly typed with the user-defined type department. Let's write code to return the list of department records to the calling client code. So as you can see, the getEmployees method returns a list of employee records, and the getDepartments method returns a list of department records. So in order to gain an understanding for how LINQ works, let's ensure that we properly understand two fundamental concepts, i.e. the concept of extension methods and the concept of Lambda expressions. So let's go to our TCP extensions project. Let's delete the class that was auto-generated by Visual Studio when we created the project. Let's add a class named extension. So in order for our extension method to work, we must make the extension class a static class. So we are going to add a method named filter. The idea here is we want a way where we can extend the functionality of any generic list that is strongly typed with any C# data type, including user-defined types. We can achieve this by creating our own extension method. So for example, if we want to filter employee records by criteria that we are able to specify through a Lambda expression on a generic list that is strongly typed as employee, we can do this through our filter extension method. This will be demonstrated in the calling client code in a bit. So how do we create our own custom extension method? So I'll first create the method signature for the filter extension method. First, notice that our method, like the class in which it resides, must be static, which is achieved by including the static keyword in the relevant extension method's method signature. So if we look at the first parameter in the filter method's method signature, we can see that we are using the this keyword preceding the data type of the first parameter, which is a generic list of type T. The this keyword in this context indicates to the compiler that the relevant method can be called on an object of the data type of the relevant parameter. In this example, that is a generic list which contains a type T placeholder. As we know from the video series on C# generics, a developer is able to pass a data type argument to the parameter of type T, which can be any C# data type, including user-defined types. The data type specified will be chosen depending on the requirement that needs to be met by the calling client code. We'll demonstrate the consumption of client-side code for the filter extension method in a bit. So let's look at the second parameter, which is of the delegate type func. For more information about the func delegate type, please view a video created by this channel on this topic. A link to this video is available below in the description. The first data type parameter passed to the func delegate type represents the first data type of the first parameter of the method referenced by the relevant argument passed into this parameter. The last parameter in the func delegate type definition is the return type of the method referenced by the argument passed into this parameter. So the first parameter passed into the func delegate is of type T, and the second parameter is of type bool. Note that a predicate delegate type can be used to define method definitions for a method that returns a Boolean value. So we could replace the func delegate type with a predicate delegate type. Let's use the func delegate type, but please note that we could also achieve the same end using the predicate delegate type. And as you can see, this method will return a list of objects of type T to the calling client code. So let's complete the logic for this method. Let's implement the code for the filter method. So basically, we are looping through the list on which the filter extension method is invoked. We are then adding its elements to a new generic list, also of type T. Whether or not we add this list item is based on the Boolean value returned by a method reference passed into the second parameter of the filter method. So the relevant method reference is stored in the argument passed to the parameter named func. As you can see, the method that the variable named func references accepts an argument of type T. So we are passing in each item stored in the calling client's list, which is the generic list on which calling client code will invoke the filter extension method. If the method that the func variable references returns true, the item stored in the iterated list is added to a new list. We then return the new list containing the filtered items to the calling client code. So this effectively means that the calling client code is able to use our filter method to filter any generic list based on a method created in the calling client code. This method created in the calling client code will contain the logic for filtering the relevant generic list. A reference to this method will be passed into the second parameter of our filter extension method and must adhere to the method definition represented in the second parameter of the filter method, i.e. the definition represented in the func delegate type. So we are now going to implement the calling client code, and you'll see that the method passed into the second parameter of our filter method will be an anonymous method, i.e. a method that is not named. This method will be expressed as a lambda expression. We'll now see how we are able to filter a generic list using our filter extension method through calling client code in the main method of our application. Right, so let's go to the .NET Core Console project and write the calling client code in our main method. Firstly, let's reference our two standard library projects from our .NET Core Console project. So let's right-click the Dependencies node in the .NET Core Console project and tick TCP data as well as TCP extensions. So let's test our filter extension method. In a bit, I'll further elucidate why it is important to understand extension methods and lambda expressions with regards to LINQ. Through the magic of how extension methods work in C#, we should be able to call the extension method on any generic list object. So let's define a generic list that is strongly typed as the employee user-defined type. So we have a red squiggly line under our generic list type definition. So to fix this, we need to include a directive at the top of our code to the system.collections.generic namespace. We can see that there is a red squiggly line under the code that strongly types our generic list as the user-defined type employee. So to fix this, let's include a directive at the top of our code to the TCP data namespace. Great! So through the magic of extension methods, we should see the filter method appear in the IntelliSense drop-down list when we add a dot after the employee list variable. Okay, so why are we not seeing the filter method appearing in our IntelliSense drop-down list? The reason for this is because we haven't included a using directive to the appropriate namespace. So let's include a using directive at the top of our code to the appropriate namespace, i.e. TCP extensions. So now if we add a dot immediately after the employee list variable, the magic of extension methods is revealed to us, and we can see our filter method in the IntelliSense drop-down list. So note that when we open brackets to pass in appropriate arguments to the filter method, we see that only one parameter is required. This parameter was the second parameter we defined for this method. So why is the first parameter in the filter method not listed when we open the brackets in this way? Well, the answer to that question is this is how extension methods work. The consumer of the code, i.e. the calling client code, does not need to pass in the first parameter. This is automatically handled behind the scenes, as it were. By default, the first parameter is the object on which the relevant extension method is invoked. So in this case, the list of employees stored in the employee list variable is passed into the filter method into this parameter automatically. So if we look at the filter extension method, we can see that this keyword precedes the definition of the first parameter. The this keyword in this context is telling the C# compiler that the argument passed into this parameter is the object on which the relevant extension method is invoked. So we have access to the argument passed into the first parameter automatically. Okay, so the second parameter accepts a delegate object that points to a method that needs to be created on the calling client. So this method that we'll create essentially tells the filter method how we want our list filtered. So we are able to define this method in the calling client code through the use of a lambda expression. A lambda expression is a concise way to represent an anonymous method. If we look at the definition of the relevant delegate parameter, we need to define a method that accepts an argument of type T and returns a Boolean value. So the C# compiler has enough information to infer that the intended type for type T is employee in this context. We are calling the filter extension method on a strongly typed generic list. The generic list is strongly typed with the employee user-defined type. So say we want to filter our employee list based on the value of each relevant employee item's isManager property. We want to filter the list where we only want to return those employee records where isManager is true. So we want to return all the records from our list where the relevant employees are managers. So to achieve this, we can pass in this lambda expression. Here we are telling the filter method how we want our list filtered. Let's write code to print the results to the console screen. Right, let's run the code. Okay, so we have no data. We of course need to populate our employee list with data. So let's assign the value returned from data.getEmployees to the employees list variable. Right, let's run the code. Great, and you can see that only the employee records where the relevant isManager property value is set to true are returned to the calling client code. Great. And we can of course inject the converse of this logic into our filter method through the relevant lambda expression like this. So we are now saying we only want to bring back employees who are not managers. Let's run the code. Great. And for good measure, let's modify our lambda expression so that the filter method only returns employees that earn less than $50,000 a year. Great. And because we have used generics for our filter method, we can call the filter method on a list of various C# types, including user-defined types. So let's prove this and call our filter extension method on a list of departments. Let's filter the departments based on the department's short name. So let's bring back the Finance Department and the Human Resources Department. Great! Let's bring back only those departments with IDs greater than 1. So the point of this is to show you the flexibility that the combination of extension methods and Lambda expressions create when writing the calling client code. The combination of extension methods and Lambda expressions not only provide this flexibility, but at the same time ensure that the calling client code is clean and concise. Once we understand how extension methods and Lambda expressions work, they are incredibly powerful tools. So, how do extension methods and Lambda expressions work in relation to the topic of this video, LINQ, Language Integrated Query? Extension methods and Lambda expressions are fundamental to how LINQ is implemented in C#. The enumerable class and the queryable class are two static classes that contain extension methods. The enumerable class and the queryable class are both members of the system.link namespace. So to gain access to the extension methods provided through LINQ, we can simply include a using directive to the system.link namespace. Without including a using directive to the system.link namespace, you can see that we are not able to access the where extension method provided by LINQ to perform our filtering operation on a collection that implements the IEnumerable interface. So let's include the system.link namespace. We now have access to LINQ's where extension method, so we can now replace our custom filter extension method with the where LINQ extension method like this. We don't need to create our own filter extension methods to perform such queries on our data. LINQ has got us covered for this. LINQ also provides us with a SQL-like query syntax. So for example, if we wanted to produce a query result by joining selected fields from data selected from our collection of employee objects with selected fields, or field in this case, from data in our collection of department objects, we can use LINQ query syntax to perform our inner join operation on these two collections of data, like this. In the LINQ query, we want to include the department long name field so that we can have a descriptive name for our department in our results set rather than displaying a result that only contains the department ID, which is available in the employee type. So we can achieve this result by using the join clause in a LINQ query to perform our inner join on our collection of employee objects with our collection of department objects. We have the department ID property in the employee type, so we can join using this department ID property in the employee type to the ID property, which is a member of the department type. So say we were to write the equivalent query using Transact SQL against the SQL Server database that contained an employee table with the same data schema as our employee type and a department table that contains the same schema as our department type. The Transact SQL query syntax would look something like this. We are using an inner join to join data in an employee table with data in a department table. We are able to make the join because the employee table contains the department ID, which can be joined in our query the ID of the department table. So you can see the similarities in syntax between the Transact SQL syntax and the LINQ query syntax. The LINQ query is dealing with objects encapsulating the employee and department records. The employee list collection is like the employee table, and the department list is like the department table in this particular context. We have a select clause, a from clause, and a join clause in the syntax for both the LINQ query and the Transact SQL query. However, the from clause in the LINQ query appears at the beginning of the query, and the select clause in the LINQ query appears at the end of the query. So there are differences in the ordering of the clauses when comparing the syntax of the Transact SQL query with the syntax of the relevant LINQ query. An advantage of LINQ is it can be leveraged in our C# code to query data in a standardized way that is independent from the format of the underlying data source. The data source could be a MongoDB database, a SQLite database, a SQL Server database, etc. This will not affect the syntax of our LINQ queries. So the object layer provided by LINQ can be used for abstracting our queries of the data from the underlying data source. And by using LINQ, we also have the added advantage of compile time, strong typing, and the type checking provided by the C# compiler. Let me draw your attention to the select clause. We are able to return the data as an IEnumerable collection of anonymous types. We are assigning the collection returned by the LINQ query to a variable preceded by the var keyword. Beginning with C# version 3, variables that are declared at method scope can have an implicit type var. Through the use of the var keyword, the C# compiler is able to infer the types included in the collection returned from the query. So we are able to return a collection of objects that are of an anonymous type that we have defined directly within the LINQ query. Anonymous types provide a convenient way to encapsulate a set of read-only properties into a single object without having to explicitly define a type first. You can see how the use of anonymous types can provide the developer with flexibility and convenience when constructing relatively complex queries. Note that Microsoft recommends using the query syntax where possible as opposed to using relevant extension methods for the same purpose. This is because of the readability advantage provided in the relevant query syntax. There are, however, times where you'll need to use appropriate extension methods included within the LINQ namespace, because some functionality in LINQ does not have a query syntax counterpart. For example, if we wanted to calculate the average salary for all employees, we would need to use the average extension method like this. The same applies if we wish to query for the highest salary from a list of employee records. We would need to use the max extension method like this. This functionality cannot be performed through the use of query syntax. But where possible, query syntax is preferable due to the code readability advantage that this syntax provides. I hope you've enjoyed this video, which provides an introduction to LINQ. This video was created to help with the understanding of the fundamentals of LINQ, the advantages that LINQ provides, and how we are able to implement basic LINQ queries in code. LINQ provides us with an integration of query capabilities directly into the C# language. It is a very powerful technology that decouples query logic from relevant types of underlying data formats. LINQ provides a layer of abstraction that provides the developer with easy-to-implement syntax for querying collections of objects. The relevant collection types must implement the iQueryable or generic iQueryable interface or the iEnumerable or generic iEnumerable interface. Note that the iQueryable interface inherits from the iEnumerable interface, and the generic iQueryable interface inherits from both the iEnumerable interface and the generic iEnumerable interface. A suite of extension methods and query syntax are made available to C# developers, which provide flexibility when constructing powerful, readable queries against data encapsulated within appropriate C# collections. This video is a basic introduction to leveraging LINQ in the C# language. In the next tutorial, we'll delve deeper into this subject matter. Hi, and welcome to the second part of a video series on LINQ. This video is also the second part of the 7th tutorial in an advanced C# course. LINQ stands for Language Integrated Query. In the first part of this video series, we looked at an overview of LINQ. We discussed that LINQ is the name for a set of technologies based on the integration of query capabilities directly into the C# language. In this video, we'll demonstrate examples where we'll create LINQ queries using method syntax and subsequently show how we can express the same LINQ query using query syntax. As discussed in the previous video, in this series, query syntax is recommended because the logic within the query syntax is easier to read. In this video, we'll look at code examples using the following LINQ operators: select, where, join, and group join. We'll discuss what is meant by method chaining and demonstrate an example that makes use of method chaining in the context of a LINQ query. We'll look at what is meant by deferred execution of LINQ queries and what is meant by immediate execution of LINQ queries. We'll discuss the inherent advantages of deferred execution in the context of LINQ. To further clarify our understanding of deferred execution, we'll create a code example where we'll implement deferred execution for our own custom extension method for an iEnumerable type. We'll demonstrate how the C# yield keyword is implemented in the relevant code example as part of code to implement deferred execution. At the end of the tutorial, we'll look at the join operator and the group join operator. We'll create code examples to help clarify our understanding of these two LINQ operators. In the first part of this video series, we discussed that extension methods and lambda expressions are fundamental to how LINQ works. We created our own extension method for filtering a generic list that can be strongly typed with any C# type, including user-defined types. We then demonstrated how a lambda expression can be created in calling client code, which enables the calling client code to determine how the relevant list of data must be filtered. The reason we created our own filter extension method was to help us understand the fundamentals of LINQ. LINQ functionality is encapsulated in two static classes that are members of the system.link namespace. These two static classes are named queryable and enumerable. These classes mostly contain extension methods As with the previous video in this series, I'm going to demonstrate the code examples in this video on my Mac platform. If you are using a Windows platform, the fact that I'm using Visual Studio for Mac should not be a barrier to follow along with these code examples. The code creation process is almost exactly the same experience when compared to implementing the same code using Visual Studio for Windows. So, let's create a .NET Core console project. Let's name this project link examples _1. So to save time, let's copy data-related code that we created in the previous video of this series from the appropriate GitHub repository. So please navigate to this URL in your browser to access the relevant GitHub repository. As always, all URLs referred to in these videos can be accessed through appropriate links included below in the description. So let's copy the data-related functionality from this repository to the project we have just created. So in your browser window, click the directory icon labeled TCP data, like this. Click the class icon labeled employee. Let's copy the code for the employee class from this page to our clipboards, like this. And simply paste the contents of the clipboard below the program class in our new project. Let's also copy the code for the department class like this to our clipboards. And paste the contents of our clipboards below the employee class within our new project. Let's then copy the code in the data class to our clipboards. Then paste the contents of our clipboards below the department class in our new project like this. So we have some red squiggly lines within our data class. To fix this, let's include a directive to the system.collections.generic namespace at the top of our code, like this. We are just creating throwaway code in this video to help us understand the relevant topics discussed in this video. So we are not too concerned with code neatness in this video. In our main method, let's create a strongly typed generic list that is strongly typed with the employee user-defined type. Let's name our generic list variable employee list. Let's assign the value returned from the data.getEmployees method to the variable we have just named employee list. This line of code will populate the employee list collection with made-up data that was hard-coded in the data class in the previous video of this series. Let's define a generic list that is strongly typed with our department user-defined type. Let's name our variable for this list department list. Let's assign the value returned from the data.getDepartments method to the variable we have just named department list. This will populate the department list collection with made-up data that was hard-coded in the data class in the previous video of this series. So let's create a link query that makes use of the select link operator. In order to use a link operator, we of course need to include a using directive to the system.link namespace. For this query, we want to select everything from the data stored in our employee list collection. We can do this by simply invoking the select method on the employee list object, like this. The select method is an extension method provided to us through link. We can shape our data through the use of a lambda expression like this. We discussed anonymous types in the previous video of this video series. So, the select operator returns an IEnumerable collection of objects. The lambda expression passed into the select extension method provides an instruction on how we wish to shape each item of data within the returned IEnumerable collection. This is specifically expressed through this anonymous type. Anonymous types provide a convenient way to encapsulate a set of read-only properties into a single object without having to explicitly define a type first. You can see how the use of anonymous types can provide the developer with flexibility and convenience when constructing queries. So here we are providing an instruction that we want each item of data in the returned IEnumerable collection to contain a full name property, which is a concatenation of the first name and the last name properties of the relevant employee record, and a property containing the employee's annual salary. So let's write the code to output the results of this query to the console screen. Let's see the code in action. Great! So if we want to filter this data, we can do this by chaining the where extension method to our select operator like this. Method chaining is a common syntax for invoking multiple method calls in C#. Each method returns an object, allowing calls to be chained together in a single statement without requiring variables to store the intermediate results. So the select operation will return an IEnumerable collection object. We can filter this returned IEnumerable collection within the same link query by chaining the where extension method to the select extension method. The where extension method filters the data stored in the IEnumerable object returned from the select method through a lambda expression passed to the where extension method. The lambda expression provides instructions to the where extension method on how the data must be filtered. Once the data has been filtered through the where extension method, an IEnumerable collection of results is assigned to our results variable. We are then traversing our results using a for each loop and displaying each item in the IEnumerable collection to the console screen. We discussed the var keyword, which allows for local implicit typing within methods in the previous video of this series. Please view the previous video in this series for more details. So here we are implementing LINQ explicitly using the extension methods provided by LINQ. We are using the select operator and the where operator in a LINQ query implemented using method syntax. Let's run the code. Great! We can execute the same functionality using query syntax. So let's comment out the previous code and include a comment to label this code so that we are able to refer to this code later if need be. So let's first implement the LINQ query using query syntax without the where clause. Let's run the code. Great! Let's implement the LINQ query implemented using query syntax, and this time include the where clause within the LINQ query using query syntax. Let's run the code. Excellent. And we get exactly the same result when compared to running the query that we implemented using method syntax. But we have constructed our LINQ code using LINQ query syntax as opposed to using relevant extension methods. The query syntax is more readable, and we don't need to chain our extension methods, as we did in the previous example where we chained the where extension method to the select extension method. Let's take a closer look at our query where we used method syntax versus the same query where we used query syntax. Note that standard query operators in our query syntax are converted into extension methods at compile time. So standard query operators are essentially the same as their counterpart extension methods. Microsoft recommends using query syntax as opposed to directly implementing the relevant extension methods where possible. As discussed, this is due to the readability advantage inherent in the query syntax. There are times when you will need to use extension methods directly where equivalent query syntax is not available. We looked at a few examples of this in the previous video of this series. For example, using aggregate functionality, like for example finding the average, min, or max annual salary for a collection of employee records. We would need to use the respective average, min, or max extension methods to calculate and return the relevant values. The developer is able to execute LINQ queries with deferred execution or immediate execution. So let's first understand what is meant by deferred execution. Deferred execution means that the evaluation of an expression is delayed until its value is required. This improves performance because only necessary executions are carried out, i.e., at the point where the relevant value is required. Let's use our last query example to illustrate this point. So when we first assign the value returned by our query to our results variable, the query is not executed. It is only when we traverse the items in our results variable that the actual execution takes place, i.e., with each iteration of the for each loop, an execution is performed, whereby the relevant item is evaluated and returned from the collection. Another advantage of deferred execution is that an update to the relevant data collection will immediately be reflected in the results. So, for example, let's add a record to our employee collection. Note, the salary for this new employee is above 50,000, so this employee should appear within our results. Let's run the code. And you can see that this is proof that the results are evaluated within the for each loop, and the query itself is not executed at the line of code where the relevant query is located. The execution of the query is deferred until the results are traversed within the relevant for each loop. To further understand the concept of deferred execution, let's create a code example where we'll implement deferred execution for our own custom extension method for an IEnumerable type that is strongly typed as the employee user-defined type. Let's create a static class named enumerable collection extension methods. Let's create a static method within the static class that we have just created, and let's name this method getHighSalariedEmployees. We discussed extension methods in the previous video for this video series. For more information on extension methods, please access a link to this video. As discussed, a link to this video is available below in the description. So let's implement the code for the getHighSalariedEmployees extension method, like this. Note the use of the yield keyword. You can use a yield return statement to return each element one at a time. The sequence returned from an iterator method can be consumed by using a for each statement or LINQ query. Each iteration of the for each loop calls the iterator method. When a yield return statement is reached in the iterator method, the relevant value in the IEnumerable collection is returned, and the current location in code is retained. Execution is restarted from that location the next time that the iterator function is called. Let's go to our main method and implement a query that calls our extension method on the employee list collection. Let's copy and paste the code that we have already written to traverse the results and output the relevant data. And let's add another employee record to the employee list collection as we did before. Let's run the code. And you can see that the new employee record is reflected in the results. The results are kept up to date due to deferred execution. Note that deferred execution reevaluates on each execution, which is known as lazy evaluation. The converse of deferred execution is immediate execution. Immediate execution means the relevant query is executed immediately. To execute a query immediately, we need to apply an appropriate toConversion method to the query. So let's copy the previous code example. Let's uncomment the relevant code. Let's change this code so that the query executes immediately. We can use the toListConversion method for this purpose. We are using query syntax here, so in order for us to use the toListConversion method, we first need to wrap the relevant query in brackets, add a dot, and then the toListConversion method. We are explicitly typecasting the IEnumerable value returned from the query to the list type through the implementation of the toListConversion method. We are also executing the query immediately. Let's uncomment the rest of the relevant code for this example. And let's run the code. You can see that the execution of our query is immediate, because this time, after we've added a new employee, the query has not been evaluated again to include the new employee record in the results. This is, of course, why the new employee does not appear within the results output to the screen. This proves that our query has executed immediately at the line of code where the query is located. And remember that query syntax does not support toOperators, so we need to wrap our query in brackets, as we have done here, and call whichever toMethod is appropriate, for example, toList, toArray, or toDictionary. By calling the relevant toMethod, in this case the toList method, we are causing our query to execute immediately. Without the toConversion method, the relevant query execution would be deferred until the relevant results are iterated. So let's move on to the join operator, and then we'll look at the group join operator and highlight the difference between these two join operations. In the previous video in this series, we looked at the join operator and discussed how we can perform an inner join on two IEnumerable collections using a LINQ query. So here we have two collections that we wish to join. In this specific use case, we need to include a descriptive department name in our results displayed to the user. We only have a department ID field in our employee type, so in order to merge the properties from our employee type with the relevant property from our department type, we need to join records of type department that reside within our department list collection with records of type employee that reside within our employee list collection. We can do this by matching the ID field in the department records that reside in the department list collection with the department ID property of employee records that reside in the employee list collection. We can do this through LINQ by using the join operator. Later, we'll demonstrate a join operation, but using the group join operator. We'll also discuss the differences between the join operator and the group join operator. Let's look at the relationship between the collection of department records with the collection of employee records. Department records have a one-to-many relationship with employee records. A specific department can have many employees as members. A specific employee cannot belong to more than one department at a point in time. Data collections can also have one-to-one relationships with one another or many-to-many relationships with one another. So in this example, we are going to look at how we can use LINK to implement a join operation between two collections of records that have a one-to-many relationship with one another, i.e. one department to many employees. So let's implement a query that joins the department list collection with the employee list collection, where the ID property of the relevant objects of type department match the department ID property of the relevant objects of type employee. So the syntax for this LINK query would look like this, when we implement the join operation using method syntax. So to join department records to appropriate employee records, we can use the join extension method and invoke the extension method on the department list collection. The first argument we need to pass into the join method is the collection on which we want to join the department list collection. So we pass in the employee collection object here. The second argument is the key from the outer collection, the department list collection. So the outer join key is the ID property that resides in the department type. We can express this argument as a lambda expression like this. The third argument is the inner join key, which is the department ID property which is a member of the employee type. We can express this argument as a lambda expression like this. So we are joining on the ID property which is a member of the department type with the department ID property which is a member of the employee type. We can define an anonymous type where we are able to shape the data for each item in an IEnumerable collection that we want returned from the relevant query. Here we are defining an anonymous type within our LINK query that includes the employee full name, which is a concatenation of the employee's first name and last name, the employee's annual salary, as well as the relevant department object's long name property. The long name property will give us a descriptive department name in our results. We are including the department type's long name property in the relevant anonymous type. This is the whole point of joining the department list collection with the employee collection, so that we are able to include a descriptive department name within our results. We only have the department ID as a member of our employee type, so if we only returned results from the employee list and wanted to include department information, we would be restricted to the department ID property, which is an integer value and is unlikely to be meaningful to a user. Let's run the code. Great! But as discussed, where it is possible to use query syntax rather than method syntax for our LINK queries, we should use query syntax because the logic expressed in the relevant query is far easier to read. So let's write the same query using query syntax. As you can see, it is far easier to read, and it is also similar to query languages with which we may already be familiar, for example, Transact SQL. Let's express what a similar query in Transact SQL might look like. So let's imagine that we have a table in a SQL Server database that could map to our employee type. Let's say this table has the same name as our employee type. Let's also imagine that we have a table in the same SQL Server database that contains a table schema that could map to our department type. Let's say this table has the same name as our department type. So the Transact SQL would look something like this. You can see how the from clause, the join clause, and the select clause are implemented in both the link query syntax and the Transact SQL syntax. Even though the link query contains the same clauses in a different order to the comparative clauses in the Transact SQL query, for someone who is familiar with Transact SQL and not necessarily familiar with link query syntax, this link query syntax at a glance should be fairly easy to understand. So the point here is that link query syntax is similar to query syntax with which many of us will already be familiar. So this makes the implementation of link queries using query syntax more intuitive. As discussed, the link query syntax is also more readable than the equivalent link query implemented using method syntax. So the key takeaway here is to use link query syntax rather than method syntax where possible, because it is more intuitive to implement and easier to read. Let's run the code. Great. So let's look at the group join link operator and why we might want to use the group join operator in our link queries. We have just performed an inner join using the join operator. This query will only return those records based on the ID property of relevant objects of the department type in the department list collection, matching with the department ID property of relevant objects of the employee type in the employee list collection. Diagrammatically, an inner join query can be represented like this. What if we wanted to return, through a link query, all the department records in our department list collection and only employee records where the department ID property of employee objects in the employee list collection match the ID property of department records in the department list collection? So if we were to write the Transact SQL version of this query, it would look something like this. We would use a left outer join to achieve the desired result. This query would bring back all department records, but only those employee records where the relevant employee records department ID values match the ID property of the relevant department records. So, diagrammatically, we can represent a left outer join query like this. So let's look at the diagram representing an inner join operation and compare the diagram to the diagram representing the left outer join operation. So let's use our group join operator in a link query to return all department records from the department list collection, but only the employee records from the employee list collection with a department ID property that matches an ID property of a department record in the department list collection. So here we are implementing our query using method syntax. You can see the implementation of the group join operation using method syntax is very similar to the way we implemented the join operation in the previous example. Let's run the code. Note, the way we have structured our output is clearly different when outputting the results of our group join query when compared to the way we structured our output of the results of our join query. But note that at the moment the same join between department records and employee records has occurred. The reason for this is not because the group join and the join operators perform the same type of join operation. It is because currently each of the records in the employee list collection match with a department record in our department list collection. Let's change our data to highlight a key difference in the join operation and the group join operation. Let's do this by going to the code where we have hard-coded, made-up employee and department records and added these records to their respective collections. Let's ensure that the technology department, which has an ID of 3, does not match with a department ID property of any of the employee objects in our employee list collection. We only currently have one employee that is in the technology department according to our data. Let's change the relevant department ID so that there are no employees that are members of the technology department. So let's change this department ID property. Now, no employees are members of the technology department according to our data. Let's run the code. So you can see our technology department record is being returned along with all the other department records in the department list collection, even though its ID property doesn't match the department ID property of any employee records stored in the employee list collection. So simply put, department information for departments that contain employees are included in the query results, and departments that don't contain any employees are also included in the query results. In this example, the technology department is returned even though it contains no matching employee records. So here we have performed a left outer join query using LINQ's group join operator. So let's rewrite this LINQ query using query syntax. You can see here that the group join extension method does not get explicitly called when we implement our query using query syntax. The into keyword is used within the query to create a group of employees for each department. So as discussed, LINQ query syntax does not match exactly when comparing LINQ query syntax to familiar query languages like Transact SQL. But in many ways, it does resemble a language like Transact SQL. In this sense, LINQ query syntax is more intuitive to implement than method syntax when implementing LINQ queries. And just to labor the point, as discussed, it is also better to implement LINQ query syntax for our LINQ queries than implementing method syntax for the same purpose because of better readability. Let's run the code. Great! And we get the exact same result as when we ran the same query that was implemented using method syntax. Now that we have changed the data so that the technology department does not match with any employee records, let's run our join operation that we created earlier. Notice that the results of the join operation doesn't include the technology department. This is because the join operation performs an inner join, and with the group join operation, we are able to perform a left outer join operation. So let's comment out our join query and uncomment our group join query. And for good measure, let's run the code again. And as you can see, the technology department is now included in the results displayed to the screen, even though the technology department does not have any matching employee records. Great! So the left outer join operation returns all records from the outer left collection in the query, but does not return records from the inner collection, where the inner collection records do not match any of the outer collection records. So if there were employee records in the employee list collection that did not match any of the department records in the department list collection, these employees would not appear in the results outputted to the screen. We can prove this. Let's change the department ID of this employee record where the first name property is Bob and the last name property is Jones. We have changed the department ID property for this record to 6, and there is no matching department record, i.e. no department record has an ID of 6. Let's run the code. And you can see that the employee record with first name Bob and last name Jones does not appear within the results. However, even though the Human Resources Department has no matching employee records, it is still included in the results outputted to the screen. Great! Let's add Bob Jones back into the Human Resources Department like this. And let's run the code. Excellent! So hopefully this made it clear how we are able, through LINQ, to use the join operator to perform inner join queries between two object collections, and how we are also able to perform left-outer join queries using the group join operator. Hi, and welcome to the third part of a video series on the LINQ technology using C#. This video is also part of the 7th tutorial in an advanced C# course. LINQ was introduced with C# version 3, which was released on the 19th of November 2007. LINQ stands for Language Integrated Query. In this video, we are going to focus on code examples that make use of several LINQ operators. The code examples demonstrated in this video will hopefully help us gain an understanding of a broad array of operators that are made available to us through LINQ. We'll learn how we can use these operators to query and transform data. This quote from the Microsoft Docs provides a basic definition of standard query operators and can be found at this URL. The standard query operators are the methods that form the LINQ pattern. Most of these methods operate on sequences, where a sequence is an object whose type implements the generic IEnumerable interface or the generic IQueryable interface. A lot of the more frequently used query operators have dedicated C# keyword syntax that enables them to be called as part of a query expression. As discussed in the previous video in this video series, it is advantageous to use query syntax rather than method syntax where possible because query syntax is more readable. Note that query expression clauses are translated into calls to query methods at compile time. For a useful tabular representation of standard query operators that have equivalent query expression clauses, please navigate to this URL. We discussed what is meant by deferred execution and immediate execution in the previous part of this video series. For a useful tabular classification of operators in terms of deferred execution or immediate execution, please navigate to this URL. For additional information on deferred execution versus immediate execution and method syntax versus query syntax, please view the second part of this video series. So to gain an understanding of several useful LINQ operators, let's create a few code examples. As with the previous video in this series, I'll be demonstrating these code examples on my Mac platform using Visual Studio for Mac. The code creation process for these code examples is almost exactly the same process as creating the equivalent code examples on a Windows platform using Visual Studio for Windows. The fact that I'm using Visual Studio for Mac should not be a barrier for a learner to follow along with the creation of these code examples. So, let's start by creating a .NET Core Console project. We created a project in the previous video named LINQExamples_1. Let's name this project LINQExamples_2. In order to save time, let's copy data-related classes that have already been created in the previous videos of this series and incorporate these classes into our new project. These classes contain class definitions for an employee and a department record as well as code that adds several made-up objects of type employee and department to their respective collections. As in the previous parts of this video series, we can then use these collections of strongly typed objects in our LINQ query examples. So to copy the relevant code, let's navigate to this URL, i.e. to a GitHub repository that was created in the previous video. Let's click on the directory icon labeled LINQ examples_1. Then let's click on the file icon labeled program.cs. Let's copy the employee class to our clipboards. And paste the contents of our clipboards within the new project that we have just created. Let's copy the department class to our clipboards and paste the contents of our clipboards below the employee class within our new project. Lastly, let's copy the data class to our clipboards and paste the contents of our clipboards below the department class within our project. So in the previous video, we looked at the following operators: the select projection operator, the where filter operator, the join and group join operators. In this video, we'll create code examples that implement the following operators. We'll start by looking at the following sorting operators: order by descending, then by, and then by descending. We'll then look at these grouping operators, group by and toLOOKUP. We'll then look at these quantifier operators, all, any, and contains. We'll then look at the following filtering operator, of type. Note that another example of a filtering operator is the where operator. We have looked at the where filter operator in the previous parts of this video series. Lastly, we'll look at the following element operators: element at or default, first or default, last or default, single, and single or default. We'll look at even more LINQ operators and create code examples in the next video. The next video will be the final video in this video series on LINQ. Right, let's get started. So let's start by looking at the data-related classes that we copied from GitHub. We have the employee class, which provides a definition for an employee record. We have the department class, which provides a definition for a department record. We have the data class that contains code where lists of hard-coded, made-up employee and department objects are added to their respective collections within their respective methods and returned from their respective methods. In the previous video in this series, we looked at join operators, namely the join operator and the group join operator. So in the context of join operations, the department collection has a one-to-many relationship with the employee records in the employee collection. This simply means that one or many employees can be members of a specific department. A specific employee can be a member of only one department at a point in time. So let's go to our main method. We can use the data.getEmployees method to return a collection of made-up employee records. Let's use this method to assign the relevant collection of employee records to a local variable named employee list. The employee list variable is defined as a generic list that is strongly typed as employee. So here we have red squiggly lines because we need to include a using directive to the system.collections.generic namespace. Let's use the data.getDepartments method to return a collection of made-up department records that have a one-to-many relationship with the relevant collection of employee records, and let's assign the relevant returned collection of department records to a variable named department list. The department list variable is defined as a generic list that is strongly typed as department. So let's get into the creation of our examples. Sorting operators. Order by. So let's create an example for the order by operator. In this example, we want to return all employee records from the employee list collection and order by department ID. To make things a little bit more interesting, let's say we want to include the department name within our outputted results. The problem here is that the department name does not exist in the employee type, so we need to join the employee list collection to the department list collection so that we can include the department name in our results. We can do this by using the join operator. So let's write this query using method syntax so that we can see all the link extension methods used in the relevant query. So we first need to make sure that we include a using directive to the system.link namespace. This directive will give us access to the relevant link operators that we will be implementing in our code examples. We know that the system.link namespace contains two static classes, namely enumerable and queryable, and these static classes mostly contain extension methods. Our link operators, which are implemented in the form of extension methods, are implemented within the enumerable and queryable static classes. So this link query joins the employee list collection to the department list collection on the department ID property of each of the relevant employee records with the ID property of relevant department records. Before we run this query, let's alter the data a bit. Let's make the employee record pertaining to Sarah Jameson a member of the technology department by changing the relevant department ID property from 2 to 3. Let's also change the department for the employee record pertaining to Jane Stevens to the technology department by changing the relevant department ID from 2 to 3. This change to the data will make the effects of our sorting operators more apparent when we view our results. So if we run the query first without the use of any order by operators, note that the data appears to us in the same order as it was added to the employee list. But now let's say there is a requirement to order our results by the department ID property in ascending order. We can do this by chaining the order by extension method to the end of the query, like this. For more information on method chaining, please view the previous video in this series. So we can pass in a lambda expression to the order by extension method to indicate that we wish to order the results by the department ID property. Let's run the code. And you can see that the results are now ordered in ascending order by department ID. If we look at the code that added each department to the department collection, we can see that the Human Resources Department has an ID of 1, the Finance Department has an ID of 2, and the Technology Department has an ID of 3. Our results have been ordered in ascending order based on the department ID property of the employee record. So we can clearly see the effects of the order by operator on our results. Great! If the requirement changed such that we needed to order our results by the department ID property in descending order, we can chain the order by descending extension method instead of the order by extension method for this purpose. Our results are now ordered by department ID in the reverse order when compared to the previous output. Great! So let's say that we want to order our results by the department ID property in ascending order and then by the annual salary property also in ascending order. So let's replace the order by descending extension method with the order by extension method in our results like this. Then let's chain the then by extension method to the query like this. We can then pass a lambda expression to indicate that we wish to further order our results by the annual salary property. The then-by extension method will order the results produced by the order-by sorting operator in ascending order. Great! And if we want to order by the annual salary property in descending order, we can replace the then-by extension method with the then-by descending extension method for this purpose. Excellent. We can represent sorting operations within linked queries that are represented using query syntax like this. Note the order by and descending keywords in the query syntax version of the relevant query. We use the order by keyword within our query to order by our first specified property. If we want to subsequently sort on other properties instead of chaining the then by extension method to our query in query syntax, subsequent properties by which we wish to sort are separated by commas. The descending keyword can follow any of the properties that we wish to sort in descending order. The default order is ascending order. So let's look at the group by and toLOOKUP grouping operators. Let's start with the group by operator. So this operator is akin to the group by clause we would apply in a transact SQL query. So we can implement the group by operator using the group by extension method, or the group and the by keywords within query syntax to perform the same operation. So let's say we wish to query the employee list collection and group our results by the department ID property. The query using query syntax would look like this. This query is simply grouping our results by the department ID property. Using method syntax, this query would look like this. In all of the link query examples using query syntax that we have looked at up till this point, in this video series, we have ended all our queries with a select operator. Notice that this query does not end with a select operator. It is important to note that a link query implemented in query syntax must either end with a select operator or a grouping operator. Notice how this query does not end with a select operator, but a grouping operation is being performed at the end of this query. So we can traverse the results of this grouping operation using nested for each loops. The outer loop traverses each group that has been created based